Today I'll be talking about Project AF8, which is a really exciting initiative. It's a collaboration between civil defence and emergency management and the science community to improve our ability to respond to a future Alpine fault earthquake. So today we're going to outline some of the fundamental science behind the Alpine fault and why we're concerned about planning for a future earthquake. And to start with, I think it's important to sort of set the context in terms of the global tectonic environment that we live in. So some of you will understand that there are tectonic plates that make up our environment around the world, and the Pacific plate is the largest of those, and it carves its way right around the edge of the Pacific Ocean. It's otherwise known as the Ring of Fire, and New Zealand sits astride the Pacific plate interface with the Australian plate right down in the South Pacific. So the plate boundary carves its way right through New Zealand. In the northeast of the country we have a subducting plate, which means that one plate, the Pacific plate, is diving down beneath the Australian plate, and when it does that it starts to melt and up comes magma and causes volcanoes right through the central North Island. And then the plate boundary continues down off the southwest coast of New Zealand into another subduction zone, which has the opposite sense of motion. So it's the Australian plate diving down beneath the Pacific plate. And in between the two is a very long and linear plate boundary fault called the Alpine fault, and that's what we're talking about today. So the Alpine fault is an 880 kilometre long structure which carves its way right down the western side of the Southern Alps. And it was discovered back in 1850 by a guy called Harold Wellman, who was a very intrepid geologist. He did a huge amount of field work through the west coast of the South Island, and he discovered that a particular rock type in the southwest of the country, you can see circled in yellow, emerged again up in the northwest part of Nelson. And he knew that these two rock types had once been adjacent to each other, but through motion across the Alpine fault had been separated over many millions of years. And this happens through earthquakes which move one side of the fault up to 10 metres at a time, progressively towards the northeast. So this is what the Alpine fault looks like from above. This is the fault carving its way down towards Milford Sound as it goes offshore at Milford Sound. And here we find evidence for past earthquakes on the Alpine fault. This is a location called John O'Groats, and some work which I'll talk about shortly has exposed an amazing prehistoric record of earthquakes going back thousands of years, which is an incredible record of past Alpine fault earthquakes. So, and this is another site. This is just further north of Milford Sound. This is a place called Hukuri Creek. And some work was done here by some scientists at GNS Science, led by Kate Clark and Ursula Cochrane and also Calvin Berryman. This is work that was done about 4 or 5 years ago, and essentially it really blew our minds in terms of what Alpine fault events had happened in the past. This is a place where the creek comes out of the Alps and it crosses into Lake Makero on an ordinary day. But when there's an Alpine fault earthquake, one side of the fault is lifted up, which essentially dams the river as it crosses the Alpine fault, and water ponds. So what Kate and Ursula and Calvin found when they came down to Hukuri Creek was an incredible record of sedimentary deposits going back over many thousands of years. Each time Hukuri Creek gets dammed by an Alpine fault earthquake, it leaves a signature of sediment. And then it happens again and again through time, as they found here. Then they're able to dig into that sediment and find little bits of carbon to date and other material like pollen and other leaves and things, and that enables them to create a clear record of earthquakes going back in time. So what they essentially found was that previously we knew of 3 or 4 Alpine fault earthquakes, the last of which was in 1717 AD. And along the top of the scale you can see time going back from today right back to 6,000 years before BC. So that's what we knew before. When they discovered John O'Groats and Hukuri Creek, and the data they got from there pushed back our knowledge of Alpine fault earthquakes way back to 8,000 years ago. And so we had data from John O'Groats and a huge data set from Hukuri Creek, which tells us that there were 27 events on the Alpine fault over the past 8,000 years. And I can't tell you how incredibly unique and amazing this data set is. For faults and earthquakes around the world, it's very rare to find evidence like this. This work has been published in Science. It's really top quality science that we've been doing in New Zealand. And what it tells us is that we have a long history of earthquakes happening on the Alpine fault. They happen remarkably regularly, going back in time. There aren't many gaps in between. So each of these little dots on the screen is an Alpine fault earthquake. The little histogram above tells us something about the uncertainty of the timing of those events. But there's very little overlap between any of these events, and this is telling us that over the last 8,000 years, these events have been happening regularly through time, and there's no reason why they should stop happening now. So, in other words, an Alpine fault earthquake is inevitable in future, and we have to start thinking about getting prepared for that. So what we think about the Alpine fault risk in a kind of a spectrum of different facets, I suppose. So we talk about the frequency of Alpine fault earthquakes, and we talk about the magnitude of those events. And that's something that Ursula Cochrane will be talking about as part of this Alpine fault science sequence of videos. And then we think about the intensity of the damage which will be done by the Alpine fault in terms of how long and strong the effects will be when the earthquake happens, and what that hazard footprint will look like, how big an area is going to be affected. And then we look at the consequences for us, for our society, for our built environment, our roads, our dams, our water networks, etc., and how we might look at reducing that risk going into the future. So Alpine fault, Project AF8, this is where Project AF8 comes in really, because we know a lot about the science. We know that there's an inevitability about the next Alpine fault earthquake, but we really need to start thinking about how we're going to deal with it. So Project AF8 has been this amazing collaboration between civil defence and emergency management and the science community to build a collective response plan for the future event. So how it works is that it's been funded by the Ministry of Civil Defence and Emergency Management. It's led by Emergency Management Southland on behalf of all of the 6 civil defence emergency management regions in the South Island. And it's funded through the Ministry Resilience Fund. And so it's a 2-year project running through till June 2018. The goal is to build a collective response plan for a future Alpine fault earthquake. And we're doing this by taking, we have 2 teams working on it. We have a response team, which is led by those 6 civil defence emergency management groups. We have a Project AF8 project manager, and we have input from the Ministry of Civil Defence and Emergency Management. And then the risk team, which involves 30 academics from around New Zealand, from 6 universities, 2 Crown Research Institutes, and 2 consulting firms. And these are the members of the steering group, so it's led by Angus McKay in Southland. I lead the science team, and John Mitchell's our program manager, and each of the group managers from the Civil Defence and Emergency Management regions is also represented on the steering group. So the way that this is structured is really around having been successful with the funding from the ministry, but also having a huge amount of input from the science community as well. So each of the bolded research programs here are putting funding into Project AF8. So the Natural Hazards Research Platform, Quake Core, the Earthquake Commission, and Resilience to Nature's Challenges primarily are supporting Project AF8 with science funding. And then you can see we're really working across the practice and policy domains to bring in all of the relevant communities and agencies that will have a stake in a future Alpine fault response. So essentially we are reaching across traditional domains of research, policy and practice. We're building on our collective strengths in order to develop this collective response plan for a future Alpine fault earthquake. So from science to societal impacts, we know a lot about the science. We know the Alpine fault last ruptured 300 years ago, and that it roughly releases big earthquakes every 300 years. The last one was in 1717 AD, so we're expecting another large magnitude 8 earthquake sometime in the foreseeable future. So the key task for the science team for Project AF8 was generating or producing a really scientifically robust scenario. That was the first task for Project AF8. So in August last year, I convened a meeting in Christchurch where 30 Alpine fault scientists came from all those different all those different institutions. And we sat in this room for 2 days trying to thrash out a robust scenario. And this built on previous efforts, but it really fed in the most up-to-date science to make it as credible as possible. So essentially those scientists were broken into 3 teams which looked at 3 different components, I suppose, of the scenario. The earthquake scientists looked at the hazards, the source of the earthquake, which part of the Alpine fault might rupture, what the geomorphic consequences might look like in terms of landslides and aftershocks and things like that, and some of the cascading hazards that will emerge after a big earthquake. So we have ground shaking, which results in landslides, and then if you have a heavy weather event, which is quite common on the west coast, that will exacerbate a lot of those impacts over the days after the event, and days, weeks and months after the event. We had a team of engineers and other scientists looking at some of the issues for the built environment, the lifelines infrastructure, and social scientists looking at the impacts and consequences for communities, businesses, and the impact on people. All of these different components of the scenario came together and are now being fed into the response planning that's been going on for the last year or so since the scenario was confirmed. And that policy and planning work stream is really looking at what we call the 4 R's in civil defence speak: readiness, resilience, response and recovery. So this gives you a bit of structure around how the work has flowed through. The risk team has developed that scenario, which was then workshopped around all 6 of the civil defence emergency management groups around the South Island, and we were doing that between November and June, November last year and June of this year. So those workshops included not just civil defence people, but also all of their partner agencies, including infrastructure companies, lifelines agencies, local and central government, industry groups, etc. So we had a huge number of participants from those partner agencies, which will be so important during an Alpine fault response. And all of this work was captured and is feeding into the development of the SAFER plan. So this is the South Island Alpine Fault Earthquake Response Plan. It's being compiled at the moment, and it will be ready in a draft form by the end of this year to then socialise and discuss with all of those partner agencies. So essentially the project goals for AF8 look at the consequences of a future Alpine fault earthquake in terms of this being a whole of the South Island issue to be dealt with. It's not just going to affect one particular part of the South Island. It's really something that we will have to work together to deal with across the traditional jurisdictions. How are we going to respond in terms of those initial response actions during the first 7 days after an event? This is the focus of Project AF8, the response during that first week after the event. Those interdependencies and priorities for response in terms of life safety, providing shelter, food, water, etc. for those affected. And how can we improve? How can we improve our emergency management arrangements around this? How can we target scientific work which really starts to look in detail at the consequences and impacts of a future Alpine fault earthquake? And how can we build better relationships between civil defence in the regions and with the national ministry structure? And how do we continue to build and develop community resilience as a key priority for Project AF8? Okay, so what was the Alpine fault scenario? What did it look like? I will just run through a couple of the main points on this. So the Alpine fault itself is 880 kilometres long. It extends almost across the whole South Island of New Zealand, but the segment of the Alpine fault that we're most concerned about is a shorter section which goes just from just off Milford Sound up to a place called Kanieri. So it's known as the F2K section, Alpine Fault Fiordland to Kanieri section of the fault. And this is the segment of the fault that we understand ruptured in 1717 AD, and the science community has a pretty strong consensus around the fact that this is the one that will probably go next when there's another Alpine fault earthquake. Before we move on, I'll talk a little bit about magnitude and impact, because there's a difference there, and I think there might be some misconceptions out in the public around what these terms mean. So magnitude is how much energy is released by an earthquake. How much seismic energy does an earthquake generate? Intensity, on the other hand, is more about the damage done by an earthquake. Because you can have a very large earthquake, but it happens in a remote location, or it's very, very deep, and it actually won't have too much impact on people and places. But intensity is a measure of the damage actually done on the surface. So magnitude is measured on a scale, what we know as the magnitude scale. This is a logarithmic scale, so each step up the scale releases 32 times more seismic energy. So let's imagine we've got a magnitude 7 earthquake. A magnitude 6 earthquake is 32 times less seismically energetic. But if you go from a magnitude 6 up to a magnitude 8, that's 900 times more seismic energy. And as you go up each step up the scale, that amount of energy goes up logarithmically. Intensity, on the other hand, is measured from 1 up to 12 on what's known as the modified Mercalli scale, where 12 is total destruction of the built environment, and each step down the scale is lesser damage. With the magnitude scale, damage is worst around the rupture zone. So we would imagine a rupture right around the Alpine fault of about 400 kilometres. That's where most of the damage will be done, the most intense damage will be done. Whereas intensity is very much related to how far away you are from the Alpine fault when this event happens. So for example, if you're in Dunedin, there'll be very different consequences compared to if you're in Queenstown or Mount Cook, for example. So this is what we imagine the intensity of damage might look like on what we call the intensity scale. So this is the best knowledge that we had in about 2013 in terms of the footprint of an Alpine fault earthquake. And you can see the intensity scale here going from 4 up to 9. As I mentioned, this is the full extent of the rupture, or where the ground will break when this earthquake goes off. About a 400 kilometre rupture zone. The damage is worst right around the outside of that zone. So you can see pockets of intensity 9, intensity 8 and 7 right around the full rupture itself. And as you move away from the rupture, you can see the damage reducing. For example, down here in Dunedin, we're getting into the intensities of 4 around the southern part of the South Island. So that's the best of our knowledge in 2013. Since then, there have been some advances in ground motion science, and we'll hear soon from Brendan Bradley, who'll be talking about his work in this area. But essentially, Brendan's had the only supercomputer in New Zealand working to simulate what intensity might be generated by an Alpine fault earthquake. And his work has been able to illuminate 3 different scenarios for intensity damage after an earthquake on the Alpine fault. So essentially, we don't really know where a rupture may begin and end on the Alpine fault. It might begin in the southern part of the fault and move its way to the northeast. It could start up in the northern part and push the energy down towards the southwest. Or it could start in the middle and push the energy out in both directions. So Brendan's work has enabled us to simulate what those 3 scenarios might look like. And I'll show you on the next slide. So this, in the top left of the screen, is the sort of generic intensity model that we had back in 2013. And then Brendan's work has enabled us to understand a bit more about those 3 different scenarios. So we've got a central rupture where the earthquake initiates here, pushing the energy out in 2 different directions. Then we have a northern rupture up in the northern part of the west coast, and with the seismic energy being pushed mainly towards the southwest. And then the third option being the initiation in the southern part of the fault and most of the seismic energy going up towards the northeast. So of course civil defence and emergency management needed something to go on. They wanted to know which was the most likely of these 3 scenarios. And so we settled on this one as the scenario earthquake that we'd be using for Project AF8. Now of course it will be different on the day. There's so much uncertainty around these sorts of things, but we selected this one primarily because it had the worst impact on the most highly populated parts of the South Island. So obviously the energy being pushed up towards the northeast part of the South Island. You can see heavy intensities actually centring on Christchurch as well as some of our other larger parts of the South Island in terms of population base. And so this was, we thought, probably the most challenging of the three scenarios to deal with from a civil defence and emergency management perspective. So this is that south to north rupture intensity map shown on the big screen here, and you can see pockets of intensities 8 and 9 around the rupture zone up and down the west coast here, but also intensities of 7 and 8 in Christchurch and up around the northern part of the South Island. So this is going to generate some significant impacts for our roading network, the Southern Alps in terms of landslides and damage from landslides around the Alps, etc. So this is a really challenging scenario to deal with. What might that scenario look like in reality? So the Alpine fault is likely to generate a surface rupture of 400 kilometres. This is a surface rupture that was produced during the Kaikoura quake, where there was around 180 kilometres of surface rupture during that event. So almost, more than double predicted for the Alpine fault. There were significant impacts generated again during the Kaikoura quake, which have taught us a lot of lessons about what the Alpine fault event will look like from a societal impact perspective. So this is one of the faults. There were 21 faults involved in the Kaikoura quake, but this is one of them carving its way across the highway and rail network and creating a reef offshore as it uplifted part of the coastline in Kaikoura. And of course, the highway was closed and it hasn't actually reopened in parts around Kaikoura, and it's been closed for almost a year. So that's had significant implications for the movement of people, of goods, of services, and also consequences for other parts of the road network where people were redirected across different sections of the network, which put pressure on, for example, Murchison and other small towns where a lot more people were coming through. They weren't really prepared for that initially, and they had to organise themselves to handle the increased demand. And this is a very old model of the flow of tourists around the South Island. This is actually back from 2006. But what it shows you is the thickness of the line shows roughly how many people are going across our state highway network. And you can see this used to traditionally be the most important route right down through Milford Sound along State Highway 1. And of course, when the Kaikoura quake happened, this was cut. So people had to start flowing down this way through the network in this direction, which has had significant implications for tourism. For example, the West Coast and the Nelson Tasman has had a 15% increase in tourism in the last 12 months as a consequence of this. What we know from an Alpine fault event will be that these Alpine passes and many parts of the West Coast will be cut off in terms of road damage, so you won't be able to get across the Southern Alps for a period of time. And just think about the consequences of that in terms of the flow of people and in terms of the response and recovery of the South Island after a large earthquake. This gives you an idea of the vulnerability of the Arthur's Pass Highway. This is the Otira Viaduct as it goes through Arthur's Pass. So there are some sections of our state highway network that are incredibly vulnerable to seismic shaking. Another issue that emerged from the Kaikoura quake was the isolation of the community and the fact that there were many tourists that were stuck in Kaikoura. About 1,200 people had to be airlifted out of the township, which had huge consequences for the response. And an Alpine fault event is likely to affect many small communities where there are high tourist numbers. For example, Franz Josef has a resident population of about 300 people, and yet they can have 5,000 or 6,000 people in that town on any given day. In fact, they had their highest peak number of tourists last summer, which was about 6,500 tourists on one day. So there are many issues for small communities who will be isolated and who may have significant numbers of visitors in their town that they will have to deal with in the short term. Another big issue is our critical infrastructure, electricity network. This is an image of Benmore Dam. This is a critical asset in the hydroelectric network in the South Island. So We anticipate that many of the lines and transformers will be damaged or down following an Alpine fault event. The dams will go into automatic shutdown when there's heavy shaking, and some of those will require power to restart. So the Benmore Dam requires power to get going again. So if the power lines are down and there is no power, then we won't be able to get those dams going again. So we'll have widespread blackouts as a consequence. There's also another vulnerability, which is our inter-island connection. So we have a cable that goes between the South and North Islands where we can push power to the North Island, and we can also take power back down to the South Island. There are significant implications for the delivery of power to the North Island, depending on the timing of this event. And in addition, electricity-reliant communications will also be damaged and down for a prolonged period. So we'll be trying to lodge or mount a response to this event when we don't have cell and we don't have a lot of other communications available, just adding significant challenges to this response. So I'm just going to wrap up with a couple of outcomes from Project AF8. These are our key goals that we want to complete by the end of June 2018. So the SAFER plan, the South Island Alpine Fault Earthquake Response Plan, will be completed, and it will be widely socialised and embedded within civil defence emergency management planning. We're building this cross-jurisdictional awareness of the fact that all of the 6 regions across the South Island will need to work very much in collaboration and work to prioritise the response in the days following this event. We're targeting science so that we build a real hazard to impact knowledge of Alpine fault consequences. And we're developing a suite of tools which will be used, videos to engage communities and agencies with into the future. And we're also building a platform for an ongoing Alpine fault engagement and research into the future as well. So I'll leave it there, and thank you so much for coming along, and I'd be happy to answer any questions that people may have.